Okay, so before we start with uniform circular motion and gravity, I want to add something on the previous video that we had. So on the video that we just had, on the lesson that we just had, we were talking about dynamics, but there is one concept that, or an application that I didn't clear it on the review, and it is in regards to the elevator. Okay, so what is elevators and the true weight of an object? So if you are in an elevator and you are moving with the constant speed or constant velocity, either up or down, doesn't really matter. So you have, on the elevator, you have three cases. The first one is when it is moving with constant velocity. It doesn't matter if it is up or down. And then the second one is when it is moving with an acceleration down. And the third one is when it is moving with an acceleration up. And let's clear a bit about the elevators. So now the elevators are like this. So you have a box where people go in, and those are tied with a system, very secure system, but pretty much what is strings that are tied with, and then they have a pulley there and an electrical panel that you control where you are going, in which floor you are stopping, and so on. So now, if you put a scale into the elevator and you step into scale, what scale is telling you, so the value that the scale is telling you is the value of force normal. So you have scale, but you have several forces. You may have a force of gravity here and a force normal. The value, the way that the scale is telling you is what is the value of the force normal. So in the case when we are moving with the constant velocity, either up or down, doesn't really matter, the free body diagram will look something like this. You being in a scale is this one here, and force normal is, since we are dealing with a horizontal surface, will be this one here. Since it is constant velocity, that means that force net is equal to 0. So now the forces that the object is experiencing are force of gravity and force net, force normal. Since this is equal to 0, then we can say that force normal is equal to force of gravity. This is not always the case. We have clarified this concept even when we were working on the dynamics. So it's not always the same. Do not try to memorize it as force normal is always equal to force of gravity. Because see what we have now. Let's suppose that the object is moving with an acceleration up, and just for simplicity, we will put a value of 2 meters per second square. So now the free body diagram will be force of gravity is this way, and force normal will be this one here. Why is it this one here? Because force net is equal to vectorial sum of all the forces that the object is experiencing. And you being in the scale, this is what you are experiencing. Now, since force net is is equal to mass times acceleration. And in this case, it is mass times acceleration because the object is accelerating up. So will be mass times acceleration. And it is positive because it is going in this direction. Is equal to negative mg plus Fn. So now Fn, as you see here, is positive because it is on the positive direction of the vertical axis. So from here we can see that force normal is equal to mass times acceleration plus mass times acceleration due to gravity. Okay, so now you see that when you are moving up, the weight that the scale is stating is increased because you are adding to mass times acceleration that is actually your weight. You are adding mass times acceleration that the object is moving up. Now, when the object is moving down, so let's say that the object is moving down with an acceleration of, we'll keep again 2 meters per second squared. The free body diagram of this situation will be something like this. This is force of gravity and this is force normal. It's less than force of gravity. Why? Because let's see now what do we have. Force net is equal to vectorial sum of all the forces that the object is experiencing. Now, since the object is moving down with an acceleration going down, then this will be negative mass times acceleration based on the second law of Newton. Force of gravity is negative as well, mass times acceleration due to gravity. So force normal will be positive because it is in the positive direction of the vertical axis. From here, we can find that force normal is equal to mass times acceleration due to gravity minus mass times acceleration that the object is experiencing. So this is what the scale will show us. So as you see here, the weight that the scale is showing when we are accelerating down is less than what is your actual weight. And this is the difference that you experience when you go either up or down. You feel more heavier, or the reading on the scale is higher when you move with an acceleration up and is less when you move with an acceleration down. And it is your true weight when you are moving with constant velocity. Is this clear? Okay, so now we'll start with that is known as the uniform circular motion. The uniform circular motion is a motion that is when the object is moving into a circle or part of the circle. So when we have something like this, when the object is moving into a circle, then what do we have is that is known as the uniform circular motion. Now let's analyze a bit the words here. Why is uniform and why circular and so on. It's called circular because it's moving into a circle or part of the circle. Now the circle is a 2D shape which each point of it is equal distance from another point outside the circle that is known as the center of the circle. Let's suppose that we are having a motion that is clockwise. So now the configuration of the vector diagram, acceleration and force net diagram will be something like this. The vector diagram or velocity diagram will be perpendicular to the displacement with the same magnitude. So the length of the vector on each point that you see here is of the vector of the velocity vector is the same. So the length, this length here is the same as this one here, the same as this one here, the same as this one here. The direction changes though. Now, the acceleration will be toward the center of the circle. So this will be the center, is known as the centripetal acceleration. So again, the centripetal acceleration changes the direction, but the magnitude is the same. Based on the second law of Newton, the force net will be toward the center of the circle, and this is known as the centripetal force. Again, it is the same magnitude, but the direction changes continuously. Centripetal force. So now, the condition for the uniform circular motion is force net is perpendicular to the velocity. As soon as force net is perpendicular to the velocity, then the object means that it's moving into uniform circular motion, which is everything in terms of the direction is changing, but the magnitude of the velocity, acceleration, or force net is the same. So the direction is changing. Even though that we call it a uniform circular motion, uniform, the word uniform means that the magnitude of the velocity, the magnitude of the acceleration, therefore the magnitude of the centripetal force or force net is the same, but the direction changes continuously. For the velocity is tangent to the circle, and for the acceleration and centripetal force is toward the center of the center of the circle. This is that is known as the configuration of the uniform circular motion. The condition for a uniform circular motion to happen is this one here. It doesn't really matter what is force net. Force net can be tension or part of the tension. It can be force of gravity or part of force of gravity. It can be the universal force of gravity, capital G, M1, M2. It can be force of friction. Now, it is tension when the object is moving into, it's tied into a string, and then you are moving it either horizontally or vertically. It is a force of gravity usually when we are dealing with the planets. So it will be capital G, mass 1, mass 2 over r squared. It is force of friction when a car is moving into a curve. Because on these cases, what we have is either everything, all of it, force tension, force of gravity, or force of friction, or part of it are equal to force net. Is it clear? There is a misconception, though, in terms of the centripetal force. Centripetal force is not a force, a unique force. It steals the identity of force net. As soon as force net is perpendicular to the velocity, then centripetal force is stealing the identity of force net, that being tension, that being force of gravity, that being force of friction. So it's stealing the identity of the force net. Now, since the object is moving into a circle and it is a uniform in terms of the magnitude, then the velocity will be 2 pi r over, that is the circumference, over time that is completing one revolution, but we call it a period. Now, the relationship between the period and the frequency is that they are inverse of each other, or the product of the two is equal to 1. Period is measured in seconds, and the frequency is 1/second, which now is taking its own identity, being known as hertz. On the other hand, the centripetal acceleration is a v²/r, which if we square up both sides, then we will have this as 4π² r/t², or 4π² r times frequency squared. Now, depend what they are giving us, we will use either this formula, or this formula. Those are formulas that you can find in the formula sheet, so you don't have to remember them. But always, force net, when it is perpendicular to the velocity, is we can say that the object is obtaining a uniform circular motion. And then from here, this takes the identity of centripetal force, which is always mv²/r, or you can say it is m4π²r/t², or you can say m4π²r times f². So this is the centripetal force. Now we can find the force net using the fact that we know how to draw the free body diagram. And then from there, we equal it with either of those formulas, and we find what the problem is telling us to do. A very common question on uniform circular motion is when we have a tension when we have an object that is tied into a string, and what we are doing is a vertical uniform circular motion. So on this case, what we study is what is the tension at the top and what is the tension at the bottom of the loop or of the circle. So since everything is happening toward the center, or a lot of things are happening toward the center, then always toward the center will be considered as positive direction. So when we draw the free body diagram at the top, what we will have is we will have the force of gravity, which is the universal force of gravity, and we will have the tension, which based on what we have said is always starting from the object going along the string, and since at the top the string is going down, then we will have this. And now, since the object is moving into a uniform or in a circle, then we know that we will have a force net that is perpendicular to the velocity, and this force net will be, the identity of force net will be stolen as the centripetal force. So now, on this case, force of gravity will be considered as positive, and tension will be considered as positive as well. And force net, which is the centripetal force, will be positive as well. However, the relationship will be something like this: force of gravity plus tension at the top. Now, force of gravity is equal to mass times acceleration due to gravity, and we said that is positive. Force net is centripetal force, and it is mv²/r. Tension at the top will be, if we evaluate this, the value of the tension at the top will be mass v²/r minus mg. You can factor out m and then see that it is m open brackets v²/r or centripetal acceleration minus acceleration due to gravity. So this will be the tension at the top, the relationship that we find the tension at the top. Let's draw the free body diagram for the tension at the bottom. So at tension at the bottom, what do we have is the object, then we have the force of gravity that is going down. Always the force of gravity is going down. And then we have tension that is at going from the object along the string. Now, even in your drawing, you can see that, or you can identify that the tension at the bottom is higher. But let's complete the calculations and see now why is the tension at the bottom higher than even the force of gravity. So since the object is moving into a circle, then we can say that force net is perpendicular to the velocity, which means that the identity of force net will be stolen by centripetal force. Now, force net, on the other hand, is the vectorial sum of all the forces that the object is experiencing at the bottom. And we don't have force normal here because the object is not on the surface, it is just moving freely into a vertical uniform circular motion. Now, since the object or force of gravity is away from the center, this is negative mg, and this is always toward the center, so it will be positive mv squared over r. So from here, the tension at the bottom will be mv squared over r plus mg. So as you see here, the tension at the bottom is higher than force of gravity and higher than the tension at the top. Question? As we said, the planets are moving into an elliptical shape or elliptical path. It's very similar. It's considered to be a uniform circular motion. And the centripetal force that is keeping the planets into the elliptical shape is the universal force of gravity that is calculated as capital G m1 m2 over r squared. Capital G is the universal constant at 6.67 times 10 to the power of negative 11. Mass 1 is mass of one object, mass 2 is mass of the other object, and r is the distance from the center to the center of the planet. So 1, 2, r is the distance from the center to the center. The common mistake that the students do is they go from the surface to the surface. What do you have to do if you have that information from the surface to the surface? You have to add the radius of the two objects. We are obligated to add the radius because the radius of the planets are very considerable. Now, in order to manage the motion of the planets, we have three laws, which are known as the Kepler's law, and they are very similar to the laws of to the Newton's laws of motion. So the very first one is that the objects are moving into elliptical shape, and what ellipse is, just to clarify it, is a 2D shape that it's a deformed circle, so that has two centers. And then the first law is stating that the planets are moving into an elliptical shape, and in one of the centers is the sun. And we are talking about planets in our galaxy. which is the Milky Way galaxy. And then the second one is that is known as the area. So the time that the planets are moving at the, I will just draw it here. So yeah, this is the elliptical shape. This is the sun. So the planet is moving here. By the time the area that the planet is obtaining at the area that the planet is obtaining at the same time interval is the same. So this area 1 here is equal to area 2 if the time that the object moves from this point, or the planet moves from this point to this point, is the same from this point to that point. And then this one here as well. So from this point to this point. So the areas that is created, that is swept as the planet is moving, is the same from the sun to the planet if they are moving at the same time interval. So time interval is the same from this to this, from this to this, or from this to this. And then the next one is that is related. It's pretty much a conversion that we do with the universal force of gravity and the centripetal force, in which we find that the distance cubed over period squared is constant for a given planet. Based on this information, you can solve every universal gravity question, and the only key here is to take the distance from the center of the object to the center of the object. This information is not necessary to be memorized, but you will be given to you. For each planet is different, and each publication actually is different, so that information will be given.